Download this code from codegive.com, link in the description below. OK, let's dive into monads. This will be a comprehensive, practical introduction tailored for software engineers, aiming to demystify them using real-world analogies and code examples. We'll cover the core concepts, motivations, and some common monads you'll likely encounter. Disclaimer: monads can feel abstract at first. The goal is not to instantly get it perfectly. The key is to see them in action, experiment with the code, and gradually build your intuition. Repetition and practical application are crucial. Table of contents. 1. The problem: handling side effects and sequencing computations. 2. What's a functor? A necessary building block. 3. Introducing monads, lifting, binding, and the return operation. 4. The monad laws, ensuring predictability. 5. The maybe/option monad, handling nullable/optional values. 6. The list/array monad, working with collections. 7. The either/result monad, handling errors gracefully. 8. The IO monad, briefly managing side effects in a pure way, Haskell-inspired. 9. Practical benefits: composability, readability, and error handling. 10. Beyond the basics: common monad transformers, brief mention. 11. Language considerations: implementation in various languages. 12. Conclusion: where to go from here. 1. The problem: handling side effects and sequencing computations. In many programming scenarios, we need to handle operations that aren't purely deterministic functions, i.e., input always produces the same output. These are often called side effects. Null or optional values. A function might return null, or undefined or none in Python, if the data isn't found or an operation fails. This forces us to constantly check for null to avoid errors. Error handling. Functions can throw exceptions or return error codes. This requires try, catch blocks or explicit error checking logic, cluttering our code. Asynchronous operations. Fetching data from a server, reading from a file, or waiting for user input are asynchronous. We need mechanisms like callbacks, promises, or async/await to manage them. State management. Functions might modify global variables or external state. This can lead to unpredictable behavior and make it hard to reason about code. Logging. Writing to a log file is a side effect. The challenge is to handle these side effects in a structured and predictable way, making our code more maintainable, readable, and less prone to errors. Furthermore, we often need to sequence these operations together. Imagine a series of operations where each step depends on the result of the previous one, and each step might fail. Monads provide a pattern for elegantly composing computations that involve these kinds of effects. 2. What's a functor? A necessary building block. Before we get to monads, we need to understand functors. A functor is a type that you can map over. That's it. Imagine a box that holds a value. A functor is something that represents that box. The map operation allows you to apply a function to the value inside the box, creating a new box with the transformed value. Concept. A functor is a type ft that provides a map, or fmap, function with the signature. In plain English, map takes a function that transforms a value of type t into a value of type u, and a functor containing a t. It returns a new functor containing the u. Example, array/list as a functor. Most languages have arrays or lists. These are functors. The map function applies a function to each element in the array, creating a new array with the results. Asterisk example, a simple custom functor, maybe / optional. Let's create a basic maybe functor, also known as optional in some languages, to represent a value that might be present or absent. Key aspects of the maybe functor. Asterisk it wraps a value that might be null or undefined. Asterisk the map function only applies the transformation if the value is present. If the value is null / undefined, it propagates the nothing state. This avoids null pointer exceptions. Asterisk get value is a convenience method, use with caution, as it circumvents the functor's protection. 3. Introducing monads, lifting, binding, and the return operation. A monad is a functor with some extra powers. Specifically, it defines two key operations. Asterisk return, or unit or of, this operation takes a plain value and lifts it into the monad. Think of it as putting a value into a box. It has the signature, where MT is the monad type containing a value of type T. In our maybe example, maybe.just acts as the return function. Asterisk bind, or flat map or chain, this is the core of the monad. It takes a function that returns a monad, and applies that function to the value inside the existing monad. Crucially, it flattens the result, preventing nested monads. It has the signature. In plain English, bind takes a function that transforms a T into a monad U, and a monad T. It applies the function to the value inside the monad T, and then flattens the resulting monad U into a monad U. This flattening is essential. Asterisk monads build on functors. Asterisk every monad is a functor, meaning it must have a map function. However, map can often be implemented in terms of bind and return. Asterisk example, extending maybe to a monad. Let's add the bind function to our maybe class. Now, let's see how bind allows us to chain operations that might return null. Notice how bind automatically handles the possibility of a null value at each step. If any operation returns maybe.nothing, the entire chain short circuits, resulting in maybe.nothing at the end. This avoids the pyramid of doom, nested if statements, associated with manual null checks. The maybe monad provides a structured way to handle potential absence of values, promoting cleaner and more readable code. 4. The monad laws, ensuring predictability. Monads must adhere to 3 laws to ensure predictable and consistent behavior. These laws aren't enforced by the compiler, but they are crucial for reasoning about your code and ensuring that your monad behaves as expected. Let M be a monad, A be a value, and F and G be functions that return monads. 1 left identity asterisk return A equals F equals FA. Asterisk lifting a value into the monad and then binding it to a function is the same as directly applying the function to the value. Asterisk in simpler terms, putting something in a box and then immediately taking it out and processing it is the same as just processing it directly. 2 write identity asterisk M equals return equals M. Asterisk binding a monad to the return function, which just puts the value back into the monad, should not change the monad. Asterisk in simpler terms, putting the contents of the box back into a box is the same as just having the original box. 3 associativity asterisk, M equals F, equals G equals M equals, X equals F, X, equals G. Asterisk when chaining multiple bind operations, the grouping doesn't matter. Asterisk in simpler terms, it doesn't matter how you group the boxes when you're taking things out and putting them into other boxes. The final result will be the same. Why are these laws important? They guarantee that the bind operation behaves in a consistent way, allowing you to reason about the composition of monadic operations. If your monad violates these laws, it's not really a monad, and you might encounter unexpected behavior. 5. The maybe/option monad, handling nullable/optional values. We've already seen the maybe monad in action. Its purpose is to handle values that might be null or undefined. It forces you to explicitly deal with the possibility of a missing value, making your code more robust. It's extremely common in languages like Scala, where it's called option, Haskell, where it's called maybe, and functional programming generally. Key benefits. Null safety prevents null pointer exceptions by forcing you to handle the case where a value might be absent. Code clarity makes it explicit when a value might be optional. Composability allows you to chain operations that might return null without deeply nested if statements. 6. The list/array monad, working with collections. Arrays and lists can also be viewed as monads. The return operation typically creates a list containing a single element. The bind operation applies a function to each element in the list and then flattens the resulting lists into a single list. This is particularly useful for dealing with non-deterministic computations or branching scenarios. Return creates a list with one element. Bind applies a function that returns a list to each element of the list, then concatenates all the resulting lists into one. 7. The either/result monad, handling errors gracefully. The either monad, also known as result in some languages or try in Scala, is used to represent a value that can be either a success or a failure. It's a powerful alternative to throwing exceptions. Concept The either monad typically has two constructors, left, representing an error, and right, representing a success. The bind operation applies a function only if the value is a right. If the value is a left, the error is propagated. Signature either L, R where L is the type of the left, error, value and R is the type of the right, success, value. Benefits. Explicit error handling forces you to consider error cases. No exceptions avoids the control flow disruption and performance overhead of exceptions. Error propagation automatically propagates errors through the chain of operations. Clear separation of concerns keeps error handling separate from the core logic. 8. The I/O monad, briefly managing side effects in a pure way, Haskell-inspired. The I/O monad is a more advanced concept, but it's worth mentioning. It's primarily used in purely functional languages like Haskell to manage side effects in a controlled way. Concept The I/O monad represents a computation that, when executed, performs some side effect, example reading from the console, writing to a file. However, the I/O action itself is a pure value. The side effects are delayed until the I/O action is actually run. Purpose allows you to write code that describes computations with side effects without actually performing those side effects until you explicitly choose to. This enables better reasoning about code, testability, and concurrency. Implementation Implementing a true I/O monad in languages like JavaScript or Python is tricky because they are not purely functional. However, you can simulate some aspects of it using techniques like thunks, functions that are executed later. 9. Practical benefits, composability, readability, and error handling. Using monads offers several practical advantages. Composability monads make it easier to compose functions that deal with side effects. You can chain monadic operations together using bind, or flat map, creating complex workflows in a clear and concise way. Asterisk readability. Asterisk monads can improve code readability by reducing the amount of boilerplate code required for error handling, null checks, or asynchronous operations. Asterisk maintainability. Asterisk by abstracting away the details of side effects, monads make code more maintainable and easier to reason about. Asterisk testability. Asterisk monadic code can be easier to test because you can often isolate the pure logic from the side effects. Asterisk error handling. Asterisk monads provide a structured and consistent way to handle errors, leading to more robust applications. 10. Beyond the basics, common monad transformers, brief mention. Monad transformers are a way to combine the behavior of multiple monads. For example, you might want to combine the maybe and either monads to represent a computation that can both fail with an error and return a potentially missing value. Monad transformers allow you to stack monads on top of each other, creating more complex and powerful abstractions. This is an advanced topic, but it's good to be aware of it. 11. Language considerations, implementation in various languages. Asterisk Haskell. Asterisk Haskell has strong support for monads built into the language. The do notation makes monadic code very clean and readable. Asterisk Scala. Asterisk Scala has excellent support for monads. The standard library includes option, either, and future, for asynchronous computations, as monads. Scala's for comprehension provides a convenient syntax for working with monads. Asterisk JavaScript/TypeScript. Asterisk JavaScript and TypeScript don't have built-in monadic support, but you can implement monads using classes or functions. Libraries like FPTS and Ramda provide monadic abstractions. Asterisk Python. Asterisk Python doesn't have direct monadic support, but you can implement monads using classes. Libraries like returns and pymonad provide monadic abstractions. Asterisk Java. Asterisk Java doesn't have direct monadic support, but libraries like Vavr, formerly JavaSlang, provide option, either, and other monadic types. 12. Conclusion, where to go from here. Monads are a powerful abstraction that can help you write cleaner, more maintainable, and more robust code. They might seem abstract at first, but with practice and experimentation, you'll start to appreciate their benefits. Asterisk practice. Asterisk the best way to learn monads is to use them. Start by implementing the maybe and either monads in your language of choice. Asterisk experiment. Asterisk try using monads in your own projects to handle side effects and compose computations. Asterisk explore libraries. Asterisk investigate libraries that provide monadic abstractions in your language. Look at FPTS for TypeScript, returns, or pymonad for Python, or Vavr for Java. Asterisk read more. Asterisk there are many excellent resources on monads available online. Search for tutorials, articles, and blog posts on specific monads and their applications. Asterisk don't give up. Asterisk monads can be challenging to grasp at first, but stick with it. The effort is worth it. Remember, the goal isn't to memorize the definitions but to understand the purpose of monads and how they can help you solve real-world programming problems. Good luck.